Hello everyone, I'm Professor Harrison, and welcome back to our module on matrix algebra for finance. Today we're covering vectors as a special case of matrices, along with the three operations that come with them: the dot product, the vector norm, and projection. We're following Ruth, a PhD student building out her matrix-based methodology for her dissertation. Today she's starting a new section of her chapter, the section where the actual operations get formalized. She sits down at her desk to get started. So far we've established what a matrix is, the notation, and the special types that we're going to encounter. We've also seen that a system of linear equations can be written compactly in matrix form, ax equals b. But we haven't yet defined what it actually means to multiply a and x together. We've written the equation, but we haven't said what the operation actually is. To get there, we need to start with one step that's a little bit smaller. We need to define vectors carefully inside the matrix framework and the building block operation that connects them. That building block is the dot product. Once we have the dot product, matrix multiplication ends up being a lot of dot products stacked together. To make this more concrete, we're going to start with a small portfolio. Ruth is studying a three-asset case: a large cap equity, a small cap equity, and a REIT. The weights vector lays out how much of each asset is held in the portfolio. The returns vector records what each asset returned over a single period. Both will be three-element vectors. Once they're set up, the portfolio's overall return comes out of a single dot product. A vector is the simplest possible matrix. A column vector is an n×1 matrix with a single column with n entries stacked vertically. A row vector is a 1×n matrix, a single row with n entries running horizontally. So we have the same notation as when we were using matrices, including the indexing, and the only difference is that one of the dimensions here is 1. When we write a column vector, we usually drop the second subscript and just write v sub I for the ith entry, since there's only one column. By default, when people say vector without saying which kind, column or row, they typically mean a column vector, and that's the convention that we're going to use for the rest of this course. So with vectors defined, the first operation we need is the one that connects two of them. That operation is called the dot product. Sometimes it's called the inner product. But either way, it basically takes two vectors of the same length and produces a single number. The cleanest way to see exactly what it's doing is on the portfolio. Let's suppose that the weight vector is 0.5, 0.3, and 0.2. 50% in large cap, 30% in small cap, and 20% in the REIT. The returns vector is 0.08, 0.10, and 0.15. So 8% on large cap, 10% on small, and 15% on the REIT. The portfolio's return is the weighted average of these asset returns. We need a way to combine the weights and the returns into a single number. That way we can get our portfolio return. This is exactly what the dot product is designed to do. The dot product of W and R multiplies the matched entries and then adds the results. 0.5 times 0.08 is 0.04. 0.3 times 0.10 is 0.03. And 0.2 times 0.15 is also 0.03. Add the three together and you get 0.10. So the portfolio return is 10% over the period. Generalizing for any two vectors u and v of the same length, the dot product u dot v equals u sub 1 times v sub 1 plus u sub 2 times v sub 2, and so on. We just multiply all of the matched products together and then sum them up to get the dot product. For now, we're keeping this simple and simply doing two vectors multiplied together using the dot product. But eventually we're going to expand this to matrices as well, where we're effectively going to be doing multiple dot products across an entire matrix. So this small operation is doing a lot more work than you would think. The dot product combines two vectors. What if we want to know something about a single vector like its size? That's what the norm does. The norm of a vector v, written with two vertical bars on each side, is the square root of the dot product of v with itself. Square each entry, sum, and then take the square root. The simplest place to see this is in two dimensions. Let's take the vector u equals 3, 4. The norm of u is the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16, and the square root of 25, which is 5. That's exactly the length of the hypotenuse of a 3, 4, 5 right triangle. The norm generalizes the idea to any number of dimensions. For a weights vector, the norm has a useful interpretation. A perfectly concentrated portfolio with everything all in one asset has a norm of 1. An equally weighted portfolio across n assets has a smaller norm because it spreads out in more directions. So the norm of a weights vector is one rough way to measure concentration in a portfolio. Lower norm means more diversification, and a higher norm means more concentration. So the norm gives us the size of a vector. The third operation tells us how two vectors relate geometrically. Projection answers the question, how much of one vector lies in the direction of another? Here's the geometric picture. Imagine two vectors u and v drawn from the origin. The projection of u onto v is the shadow that u casts onto v's direction. It's a vector pointing along v with a length equal to however much u was actually in v's direction. The formula for the projection of u onto v is the dot product of u dot v over the dot product v dot v, all multiplied by the vector v itself. The fraction in front is a scalar. It tells you how many copies of v you need to match the original component of u in v's direction. Then you multiply that scalar by v to get the actual vector. Let's take a quick two-dimensional example. Let u be the vector 4, 2, and let v be the vector 1, 1, which points along the 45-degree line. The dot product u dot v is 4 times 1 plus 2 times 1, which is 6. The dot product v dot v is 1 plus 1, which is 2. The scalar in front is 6 over 2, or 3. Multiplying that scalar by v gives the projection vector 3, 3. So the shadow of u onto the 45-degree direction is the vector 3, 3. So what exactly does our 3, 3 mean? Well, if we were to take the point 4, 2, where our original vector started from, and draw a line straight from that point up to the 45-degree line, such that it intersects that line at a right angle, it would intersect that point at exactly 3, 3. This is what we mean when we say we're drawing the shadow of our vector onto the direction of the other. It's effectively going from the tip of our vector to the closest points on the direction of the other vector. Said differently, it's how much our vector goes in the same direction as the other vector. One easy way to visualize this is to project your vector onto the x-axis. Let's say we want to project our vector onto the point 1, 0. This will effectively give us how much our vector 4, 2 is in the direction of the x-axis. What we end up getting, if you were to work through the math, is that our projection is the point 4, 0. Similarly, if you were to project onto the y-axis, the point 0, 1, you would get that the projection is simply 0, 2. So what exactly is happening here? When we project onto the x-axis, we're effectively removing all the pieces of our vector that aren't in the direction of x. We know that in the direction of x, our vector goes to the right 4, and then in the direction of y, it goes up 2. So when we remove the pieces that aren't in the direction of x, we're left with just 4, 0, and if we do the same thing with the y, we remove the 4 and we're left with just the 2. So effectively, this is just how the coordinate system is built. And when we do a projection, we're just saying, let's say that the axis now, instead of it being just the x-axis or the y-axis, let's say that it's some other vector. We want to figure out how much we're going in the direction of that vector. Projection comes back hard in Module 5 when we get to regression. The OLS estimator that we're going to derive is geometrically a projection of the response vector onto the column space of the predictors. This sounds confusing, but it means that this small operation is going to end up being a very important tool for us later. Ruth gets up from her desk. She has finished this section of her chapter. Everything she just wrote in it does more work than what it looks like at first. The dot product is going to show up everywhere as soon as the matrix multiplication ends up entering. The norm is the language that she'll use to talk about portfolio construction, and projection is the geometry that she'll come back to when the dissertation reaches the regression chapter near the end. 3 small operations all set up to compound and become very important later on. So that's vectors as special matrices. The dot product, the norm, and projection. Each operation looks small on its own, but the dot product becomes matrix multiplication, the norm becomes the language of portfolio concentration, and projection becomes the geometry of regression. These will end up being the building blocks for everything that follows.